Hello, everybody. If you are watching this, it is probably, sorry, come on, it is probably February 4th, 2019, and it is Monday, and we are talking about momentum, specifically conservation thereof, and how to solve those problems, to deal with conservation of those problems. So we learned in Lab 1 that momentum is conserved. All right, what does that mean? Well, that means that the momentum before equals the momentum after. Which I think brings up a fair question. Before and after what? So what we're really talking about most of the time are collisions. And there are two types. And you can always pause this and stop it and slow it down. Rewatch if you want. There are two types of collisions. Really, there are more, but we'll focus on these two. One called elastic, and that's full bounce, no sticking together, no deformation or anything like that. Think about it like billiard balls. Bouncing off one another. So that's a big type of collision. This type we think about a lot. Elastic, you might think that means squishy, like a rubber band or a rubber ball or something, but that's not how it's meant in this sense. In this sense, elastic means full bounce and no sticking. And pool balls, they're very, very hard. The other type of collision is, as you may have guessed, inelastic. And that's when things stick together. You saw that in a lab where we ran one cart into the other. The Velcro allowed them to stick together and become one kind of thing. So in both of these situations, if you have things bouncing off of each other, we'll try to play with that on Tuesday, or if they stick together, whatever's going on with their momentum, whatever momentum they have at the end must be the same as they had at the beginning. That is what we learned in that lab. Momentum is conserved. So we need to talk about solving cons of mom probs. I think you guys should take the time to write those words out. I'm being lazy. All right, so to do that, we're going to take a look at worksheet 2, which you should pass out right now. I'll take a minute if you want to pause the video and make sure everybody has a worksheet in front of them for worksheet 2. All right, pass those out. Okay, thank you for passing them out. Let's talk about them a little bit. Let's go to another clean page so we have more room to work. All right, so let's take a look at number 1. And we're talking about a girl shooting a gun. So when we solve these problems, first thing you're going to do is draw the situation. And then the next thing you got to do is you got to write down what you know. And then when I say draw, I mean you've got to draw the before situation and the after. You need to draw both. It's really important to get your thoughts organized and to know what sort of math you need to do to solve the physics problem. So we're going to draw the before and after. We're going to write what you know. 3, we're going to determine what we're trying to solve. And then use the fact that row before equals row after to solve problems. So let's talk about number 1. Yes, I know I'm going fast. You can stop it and pause it all you want. One of you guys should be holding the remote control, taking care of each other. Remember, rule 1, everybody love everybody. Okay, so number 1 on worksheet 2, number 1. We got a girl with a gun. So I'm not going to make any jokes about that. So the first thing we should do, we've got a before situation. We've got an after situation. And when we say before and after what? Well, before and after the gun is fired is what we're talking about. So before You've got a gun that has a bullet in the chamber. After you've got a gun and there has been an explosion, and now the bullet is traveling at a high rate of speed away from the gun. But if you ever held a gun, you know that the guns actually have their own velocity. Velocity of the gun goes backwards, velocity of the bullet goes forward. And you feel that gun slam against your shoulder if you fire a gun. All right, so we've drawn it. Let's talk about writing down what we know. We know the mass of the rifle equals 2.0 kilograms. That's about 4.5, 5 pounds. We know the velocity of the rifle equals what? 0. It's not moving. So hey, do we know the momentum of the rifle? Sure, it's 0 because 2 times 0 is 0. Do we know the mass of the bullet? Notice we got to account for all this stuff. Sure we do. It's 0.001 kilogram. Do we know the velocity of the bullet? Sure we do. It's 0. It's just sitting there in the gun. Do we know the momentum of the bullet? Sure we do. It's 0. It's that times that. So do we know the momentum total before? We do. It is 0. The rifle's momentum plus the bullet's momentum equals 0. So what does momentum of the system have to have after the explosion? That's right, 0. It's conserved. So let's write down what we know. We know the mass of the rifle is still 2.0 kilograms. The velocity of the rifle, we don't know. We're trying to find that. So let's just call it velocity of the rifle. The momentum of the rifle, I don't know. Or maybe we can find it out. We know the mass of the bullet equals 0.001 kilograms. Now we do know the velocity of the bullet. It's 150 meters per second because it takes off very fast in that positive away from the gun direction. So can we find the momentum of the bullet? You know we can. So we multiply those two things together and we end up with 0.15. And the units are these kilograms times meters per second. So wait a minute. I thought the total momentum after has to equal 0. How can it do that if the bullet has this kind of momentum? Well, that means the rifle's momentum must be negative 0.15 kilograms times meters per second. How do you feel about that? These two things have to add up to 0. The system had 0 momentum to begin, therefore it has to have 0 momentum to end. We know the momentum of the bullet. The momentum of the rifle must cancel it out, so they both equal 0, as they did to start. Are we done with the problem? No, we need to find the velocity of the rifle. We know the momentum of the bullet, of the gun, equals the mass of the gun times the velocity of the gun. We know the momentum of the gun, and we know the mass of the gun, so the velocity of the gun equals momentum of the gun divided by the mass of the gun. Do some math. You got that's negative 0.15 kilograms times meters per second. And we're dividing it by the mass of the gun, which is 2.0 kilograms. Hey, look what happens with the units, you guys. So the velocity of the gun equals, kilograms goes away, negative 0.15 divided by 2 equals, what is it? 0.075 meters per second. Does that make sense? The bullet is traveling 150 meters per second. The gun is traveling negative. The gun is traveling negative 0.0175 meters per second. Is that fast or slow? That's slow. Does that make sense? The bullet is tiny. It's very light, so it takes off super fast. The gun is relatively heavy compared to the bullet, so it just goes back a little bit. And the next problem is very, very similar, except now, instead of it being just a gun and a bullet, now you've got just a girl with safety gear and a hat on. She's awesome. She's going to shoot this gun herself. That's the universal symbol for girl. No offense, ladies. So here the deal is, you've got the bullet in there just like before, but now it's a little bit different because the after situation, you still got the girl. There's her hat, there's her hair, there's her goggles, there's her smug face. I don't know what her deal is. Then she's holding out the gun here, and now you've got, again, the velocity of the bullet going in that direction. But now instead of just being the girl or the gun firing, now you've got, if you fire a gun properly, you've got the gun pressed tightly against your shoulder. And there's a reason for that, because now the mass over here has become the mass of the bullet, sorry, the gun and the girl together. They've become one big thing. So you got to figure all of that into this. So now it's not just the mass of the gun, but it's the mass of the gun and the girl combined because they stay together. So I think you can handle this. Just apply the same approach that we just did up there and dive in and see. What do you think should happen to that? If instead it was just this 2-kilogram gun that was recoiling away from the bullet, now you've got the 2-kilogram gun and the 48-kilogram girl. That's a total of 50 kilograms with the same impulse applied. Think about that. Why do I say impulse? Because there's a change in momentum. So the same impulse is there, but now it's much more massive. What should the recoil velocity be if the gun is against the shoulder of the girl? Bigger, smaller? Should be smaller because they have much more mass. That's why you hold a gun against your shoulder tightly when you shoot guns. Not advocating for shooting guns, just saying, if you do, that's the way to do it. Okay, you guys need to dive in, take this approach, keep yourself organized, don't forget the steps. The steps are important, not just to make me happy, it's because this is how you solve problems properly. Good luck to you. Look forward to seeing you guys.